Now, classical relativity suggests if you have a spaceship that fires a missile and at some point in time the missile is traveling relative to the spaceship, we'll call it U prime, 70% the speed of light, then it measures the spaceship at 70, the spaceship measures the missile to be traveling away from it at 70%. But the spaceship might already be traveling at 0.6% the speed of light. So obviously classical relativity says that this bloke trying to look at the missile would see it as V plus U prime, and we would go 0.6 C plus 0.7 C is 1.3 C, and that is wrong. Obviously, we cannot observe anything anywhere in the universe traveling faster than the speed of light. What we're going to add is the Lorentz factor is going to basically be combined, and we don't have to worry about the derivation. It's going to add this nice little division that brings it back to always be under the speed of light. All right, so they can be getting close to the speed of light, but never equal to it. At least the observation of the missile relative to a stationary observer. Okay, so you can have a go if you want. Doc Physics does have a derivation. The links are at the top of the OneNote. You can follow. Obviously, I've just screenshot like towards the end, or maybe somewhere in the middle, where things are getting a little bit crazy. Okay, so let's get over the page. In your data sheet, okay, you have the following. Now, I should make the data sheet color red. We need to assign a few things. Now, U prime, just put underneath here, U prime is speed of object relative to V. So the easiest way to remember this is if you see a spaceship, you're seeing it as with a speed V. U prime is the speed of the missile relative to the spaceship. So if you've got some room somewhere, we'll say here's a person observing our spaceship traveling with a speed V, and then it fires a missile which it measures as U prime. So that prime is basically a different reference frame measurement. And then we would obviously want to measure U, like so. Okay. Now, I'm going to stick with the spaceship firing the missile analogy, but you could have two people traveling towards each other, away from each other, when measured from a stationary observer. So let's just have a look now at the maths. So what we've now done is we've added this new term underneath that's going to basically be, it's always going to be less than 1.3. So there's the term there. Now, it's not too nasty if you leave your velocities in terms of c, then you end up getting a c squared over a c squared, okay? And it's just going to cancel. It's 1 plus, so the 0.6 multiplied by the 0.7 comes to 0.42. When you add it together, it's 1.42, and so we get that the person would observe it to be 0.9. Now, am I missing a c? Yes, there should be a c there, 0.92 c, okay? Now, what we could do, we need to assign a convention. Let's try something else. Let's go back to the original diagram, because we've got some room on the page here. We'll do some maths. Let's put a different value. Let's just do some red text. So let's just say that V is now actually, 0.4 C, and it fires a missile, U prime. I did go backwards. Why is it not undoing? Oh, for God's sake. U prime equals 0.8 C. All right, so that would be the speed of the missile relative to the rocket ship, What does this bloke see? Let's give it a go. Write the equation out. It's in your data sheet. All you need to do is throw it down. They're traveling in the same direction, so we don't really need a convention at the moment. We're just going to add the values together. 0.4c plus 0.8c. We'll do an intermediate step just to solve a few things. So the classic says it should be 1.2. That's not the case. 0.4 times 0.8 is 0.24. No, 0.32. 1.32. That's the numerator. Sorry, the denominator. That brings it back to obeying the rules. So now all you do is 1.2 divided by 1.32. 0.909, 0.909c. I have seen students in the past do this equation all with meters per second, meters per second, meters per second, meters per second, 3 times 10 to the 8 meters per second squared. Don't do that, all right? You can see clearly this... You can very obviously visualize on the board. It's much easier if you leave things in terms of c. You're just adding a few terms and cancelling the c's underneath. If you were given speeds in meters per second, I would probably convert them to decimals of c. Okay? Now, the thing that I want to teach you now is we can always change things, points of frames of reference. What if we said that this observer could be in one of the other objects, in the other frames? If we've got 3 frames of reference here, what if I said, let's put the bloke like some weird space cowboy, yeehaw, on the missile, right? And then he looks back and he sees a spaceship. Now, to his perspective, that spaceship is going to be traveling, what number is on the screen? It's 0.6, right? That was what we started with. But I'm going to say v equals negative 0.6. So he sees the spaceship receding. So let's say that if you're in space, right, we've got no reference frame. So what's to say that he's sitting on the missile at rest, and he looks behind his shoulder and he sees the spaceship receding? Don't ask. Just... No.
Because
no.
the missile just travelling over.
Oh my gosh. Yes. Oh my gosh. I won't make the same mistake for the next class. Sorry about that. You're absolutely right. Now you're absolutely correct. The people in the spaceship see some bloke down here, but that's relative to the spaceship. That's U prime, which is now 0.6c. Thank you, Cooper. And so the question is, what would the space cowboy see the bloke receding at? Well, we already know the answer. It's 0.909. But we have done a Galilean transform. We've basically said, let's just take this observation from one of the other reference frames. So let's do that. Now, you might notice I've added a convention in this case that moving to the right is positive. Everything's moving left now. Okay, so that's what we're saying. The bloke in the first scenario said, oh, everything's moving to the right. But if you're sitting on the missile, you would say, no, everything's moving to the left. Negative 0.6, yes, thank you. That's a bad start to the lesson. U equals V plus U prime over 1 plus V U prime over C squared. Now let's put all the negatives in. Negative 0.7c take 0.6c over 1 plus negative 0.7c, negative 0.6c. Oh, look at that. It doesn't matter that we assigned left as negative. Since they're both travelling in the same direction, you get a cancely. So you end up with, let's just redo one step, negative 1.2c over positive 1.32. So you get negative 0.909c. You get exactly the same magnitude, but the completely opposite direction.
No, because you use different values for that.
8.
Oh
It's negative 0.9.
man, it's the answer on the previous page.
0.9848.
Oh man, it's this one here. Wait, it's this. Oh man, I'm having a bad day. Nothing different really. We get negative 1.3c over positive 1.42. Sorry, this is the math on the other page. We get negative, whatever the answer was on there. 92.
Well, you usually get you transfer it back into meters per second sort of that.
Yeah, well, probably not. You've done a lot of maths at this point, and so they're happy for you to leave it in terms of C. Just be careful with what the question asks.
Yep.
In the WACE exam, often they will have the answer. They expect you to write the answer in the bottom right corner. They'll have a little, V equals with a line, and then it'll say C, or it'll say ms to the negative 1. So if you see ms to negative 1, you're like, oh, okay, I've just got to convert it. Okay. All right. Have a look here. This is the weird thing. Even though we're not going towards the speed of light, we're coming back from the speed of light. We're going to subtract 0.3c from 0.6c. These two speeds are still relativistic, and the effects will still happen. So now it is not 0.3c. Okay, the numerator is 0.3c.
That's just basic maths. 0.6.
I know, but not when you're traveling really fast. Okay, so the relativistic effects of the spaceship still sees that the the traveling away velocity is actually 0.365. Okay. All right. Let's look at this one. Now, there's another equation. I have to open up my laptop, actually. There is another relativistic equation in your data sheet. And I'm trying my best not to confuse you. I want to show you that you can do this in different ways. Okay? So, at the moment, two spacecraft are traveling at 0.8c and moving apart from each other. Well, that 0.8c must be relative to this bloke here. All right? He sees that spaceship as 0.8c. He sees that spaceship at negative 0.8c. The question is, what would the spaceship see themselves as? Well, what are we asking for? We're asking for u prime. So let's just cross that out for now. And I believe, have I written it on the previous data sheet? There's another equation in your data sheet, u prime. Okay. So what we want, u prime from v. So let's set one as v and one as u. Okay. So let's go v equals and u equals. And so now u prime is always the speed measured from that which we just decided to be v. So we're going to say, what is u prime equal to? Now I'm going to assign a convention here. Let's just say that, well, I already did. V is the positive direction. So in your data sheet, there's another equation, and all it's done is it's just rearranged that equation on the other page. It's just rearranged it for u prime. You could probably sit down and think about how you would derive it. It takes too long. It's actually u minus v over 1 minus vu over c squared. Okay? So, here's where you've got to be careful with your conventions. We know that the relative speed of one ship to the other can't be greater than c. Classical says that it should be 1.6. We're going to have it pretty close to c, maybe 0.99. And it's also going to be traveling left, which we decided as negative. Okay, so the way that I've set this up and the convention that I'm using, I'm expecting a negative 0.99 something. Okay, let's give it a go. U prime equals U. Take V to be your lawful wedded husband. Up the top is negative 1.6. Here we go, 1 minus V, which was 0.8c, times negative 0.8c. Let's just tidy it up a little bit. So the top line is negative 1.6c. Now we've got a 0.64 negative that we're going to be subtracting. So what's 1 minus 0.64?
Minus negative 0.64. So it's 1.64.
It's minus minus. Oh, good. 1.64. We stick with the rules. And I think we get 0.976.
So can't you just use the base equation which we had beforehand and just switch around the values so that the person's running away at?
Oh, mate, we're singing off the same hymn sheet. This is what we're going to do now. We're going to put the bloke in the frame of reference of the spaceship. Now, in this case, I'm going to say he sees... Now, could you get a different coloured pen? And we're going to draw some dashed stuff here. So now, the bloke is at rest. He observes the spaceship is now the person, and he measured that spaceship as negative 0.8c, and the bullet that this spaceship fired is now the other spaceship because it's now going to be U prime because it was measured from the spaceship, which is the person. Ooh, it's negative 0.8c. So this is, oh look, this is going straight back to the initial question on the first page about a bloke sees a spaceship firing a missile. The only thing I've done is, it's moving to the left now, so we've just got negatives instead of positives. So, as Cooper said, if you're not happy with this U prime question, you could do a Galilean transform, which is this here, and that should say V equals, V equals negative, and just look at things from another point of view. Now let's use the equation from the previous page. V plus U prime over 1 plus VU over C squared. We're going to get negative 0.8c plus negative 0.8c. All right, so we still got the classical relativity stuff going up there. Nothing's broken yet. Ooh, who dat? I will text you later. I'm going to have to call you back. And look, we get the squares and the squares and you get the same equation, the same fraction, the same ratio. Negative, I forgot the negative over there. There's a 0.976c. Okay, now, who has room on their page? Who would like... Oh, you've got plenty of room. I gave you some room. Now let's take, with a different coloured pen, a space cowboy is now riding that spaceship. Let's take it from his point of view. Now, obviously, you could agree, Larry, if I'm travelling down the freeway and I see you go in the opposite direction, I would say, oh, Larry's travelling 200 kilometres per hour north. And Larry would say, no, that bloke's travelling 200 kilometres per hour south. They get the same magnitude, it's just a different direction. And that's what happens when you take these, when you transform into a different frame of reference. So, with a different coloured pen, the person sees the black stick figure as the spaceship. He measures that to be V equals plus 0.8c. And then the black stick figure took a measurement of the other spaceship, which is now U prime, which is the rocket from the other. Okay? Now, this is almost identical to the first question on the previous page.
chop the bottle out of underneath him, and he just dunk. Come on, you Isaac. Huh? Oh, that would be nice. Come on.
I'll go get you a Vicky from the staff room and you can have some biscuits. Guys, in the space at the bottom, you're going to do exactly the same stuff. Now it's all just positives. There's no negatives. There's no double negatives. It's just 0.8c plus 0.8c over 1 plus 0.8 squared over c. Oh, yeah, what? Yes.
I still don't understand why it's like double negative and then double positive.
So this one was a different frame. This is the bloke in the middle.
If you're the green guy, going right.
So the reason why u prime is negative 0.8c is because the initial measurement was taken from this bloke, who we've now turned into the spaceship. So now that object was taken from his frame of reference as 0.8c, but now if we turn him into the spaceship, then the missile is measured from its frame, and that's why it's u prime.
Oh, so when it's prime, what is that?
Prime is the measurement of an object from the other object that we denoted as v. So u prime is the speed of the missile relative to the rocket that we measured as travelling as v. Then we measure the speed of the rocket as u.
Oh, so when you have the prime, it's a different frame of reference.
As an observation, a measurement from a different observation, a different frame. Yes, Bongers. The spaceship. And then the other spaceship became the missile that was fired from the spaceship. He's now at rest.
He's the guy.
He's now the bloke in the spaceship. So, would you be happy that there are 3 blokes in this scenario? There's 2 blokes that are driving the spaceship, and then there's 1 bloke just sitting on a deck chair in the middle of space watching. Yeah. But initially, this guy took the measurements. He goes, oh look, a spaceship travelling that way at 0.8c. Oh look, a spaceship travelling that way at 0.8c.
The one on the left, that's u, and then the one on the right is v. Is that?
No.
No.
Let's go to, I think we have...
There are 2 moving balls inside. There's the bullet just go 2 moving balls.
Alright, here we go. Over the page. Let's do some questions.
So there are 2 walls inside of you. One of them is moving, and the other is moving.
Moon. 2 wolves. One is travelling at 0.6c. Alright, boys. Gents, here we go. What we're going to do, I want you to get 2 different coloured pens. Shh. Gents, shush. I want you to get 2 different coloured pens, and we're going to use the u prime equation and the u equation. Let's just set up this scenario. Here we have a bloke on the Earth. You've got VE for Enterprise and VD for Discovery. They are travelling in opposite directions. So take your pick. Let's say that V Discovery, that's a D, travels that way, and Enterprise travels that way. Now, again, you've got 1 as u equals, and I just decided that Discovery is now u. That's 1 measurement, and it's going to be negative 0.85c. Then this one becomes v, which is plus 0.7c. Now we want... Oh, that's a stupid question. We've just answered it. It actually answers it. Okay, that's a trick question. Now, from the reference frame of the occupant of Discovery, what would the velocity that they say? Well, that's just the opposite. So I would say v equals 0.85c that way. That's easy. Okay. Now we want to get to the relativistic stuff. So we want to answer this question down here. An occupant of the Enterprise says the Discovery was travelling at 1.55c. This is wrong. Okay, what an idiot. Let's prove that it's that number there. So we want u prime, and u prime is always measured from the object of that which was given v. So that was given v, and so u prime for this scenario is going to give me the speed of the discovery as observed from the Enterprise. There we go. The speed of discovery as observed from the Enterprise. So let's take the u prime equation from our data sheet. It's going to be, I better look at it, u minus v over 1 minus uv on c squared. I've already put my convention in that positive and negatives are in opposing directions. So u is negative 0.85c minus plus 0.7c. That's the wrong answer, the plus 1.55. Divide it by 1 minus. As you said rightly, I'll just tidy up this bracket here. You get a double negative. You'll get 0.85 times 0.7. I'm just going to do one intermediate step. We get the classical value, which is wrong, divided by 1.595. So we get negative 0.972, which is the correct answer. But if you're not happy with the u prime, let's turn this guy into a space cowboy. We're going to go put the space cowboy in the Enterprise. So here we go. I'm going to redraw my Enterprise so I can draw my space cowboy. No, it's left. Because it's from this guy's perspective, the discovery is moving left.
Yeah, correct answer is positive. Do they just have the other?
Well, that's because it doesn't have the dual material.
Well, I assigned, when I drew the diagram mention, I just forced the convention, all right? So, space cowboy, take your pick of what colour you want. Yeehaw. No.
It's the same concept.
All right, what I'm doing now, we're saying let's just take this from, let's move all of these measurements to the bloke that's in the Enterprise. In which case, I'll write it down here. The Earth now becomes the imaginary spaceship, which he measured as v equals negative 0.7c. And then the other discovery was observed from Earth. Now we'll say the missile is observed from the spaceship. Okay? And so now we want to say, well, what would u be from this bloke's reference? So now I've enabled, now I can now use the other equation that's in the data sheet. You don't need to do this. I just want you to do both, and then whichever one you're confident with using. All right, and they're all negatives again. Everything's moving left, so everything's going to have a negative. Negative 0.85c. I've done it in the wrong order. Let's try that again. Negative 0.7c. Negative 0.85. And it doesn't, again, as I'm repeating myself here, it doesn't matter that they're all left because then we get a double negative. So our denominator comes back to a positive. We get negative 1.55c over 1.595 972. Okay? Yo.
For the left side, you're pretending to be an observer from Earth and you're calculating the relative speed of D from E.
Okay, so hang on. So the black text is the bloke on Earth takes two measurements. That's why there's no prime, because both measurements are from his frame. One is V, one is U. U prime is the measurement from the object that he measured as V. So I said if that bloke's V and that bloke's U, then U prime is how this guy observes that guy.
Yeah.
Okay?
Yeah.
So that was the whole, that's V, that's U, both measured by him. prime is from the bloke that we called V. So U prime is the, what does this guy over here, how does he observe that guy? Now, let's flip it. Let's call that V, let's call that U. In which case, U prime would be, what does this guy see that guy? As an activity, you could do that, and instead of getting minus 0.972, you get plus 0.972. That's like the Larry example. I see Larry travelling up the freeway at 200 kilometres per hour north. Larry goes, no, I saw Mr. Murray travelling down the freeway 200 kilometres south. It's just changing the U and the V. Because I said my U prime and he said his U. Yeah. I said my U prime, he said his U prime. Both of our U's and V's would be from the opposite plot sitting on the side of the road with his radar gun. He goes, that bloke's travelling 100 kilometres per hour north, all good. V, 100 kilometres per hour south. The U prime is the observed measurement from the bloke that was given the title V. Write that down if you are confused. U prime is the observed measurement from the bloke that was given the speed V. Yes, Mitchell?
What's the speed of light? The speed of sound, so it's
340. Just take it as 3. It won't end up mattering.
And that's 700 reads per second. Is that relative to you?
Yeah.
I don't know.
Oh, wait.
Draw a diagram, have a go.
Oh, I know. Yeah. What's it?
So,
Wait, no, the speed of sound changes.
yeah, let's just go. Hang on. Last year I said it was 1200.
What? One way off 340.
Shut up.
Wouldn't that be kilometers?
Shut up.
Kilometers per hour?
Meters per second.
Really? That's pretty good.
That's 3.5 times the speed of sound.
Oh, 3.5. Okay. I thought you meant the speed of sound was 12.
That is okay. Pretty slow,
Now, we're going to say that the missile U prime is the 700. In which case, yeah. Okay, so yeah, we're calculating U. Okay. So classical is just the top of the equation in your data sheet. V plus U prime. Now, the answer might shock you when you do relativistic effects. What are you going to get? What are you going to get? Yeah. You'll find the denominator is going to be so close to 1 that it's not going to change because our V and U prime is nowhere near the speed of light. So let's just have a look. We'll go U equals V plus U prime over... Oh, now in this case, let's use meters per second. Because if you convert these to C, it's going to be 0.00000. So it doesn't matter whether your numerator is a very small decimal of C or your denominator is a friggin' huge number. Yes, thank you. Can anyone's Casio calculator give any
Let's go take this instrument.
decimals?
2.111 times 10 to the negative 14.
Is that the difference?
That's the...
Oh, so we basically need about 13 zeros here. 1, 2, 3, 4, 5, 6, 7, 8, 9,
Yeah, that's...
10, 11, 12, 13. Approximately.
Yeah.
And then take 1 from that. 1, subtract that. Add 1 to that.
Is the speed, is the relative speed where this starts?
That's so
still
close.
about 14.
That's
What?
so
Sorry,
close.
what'd you get?
No, it's 9.33 times
Yeah, it's 9.33.
10 to the negative 12.
Yeah.
Yeah, it's square the speed of light or something.
Nah, I squared the speed of light.
Speed of light is 9 times 10 to the
Oh,
16.
I didn't times it down.
Oh, you fucking idiot! Someone throw some paper at him. No. All right. Well, okay. Doesn't matter. Point is,
It's a small number.
it's going to be 0. The Lorentz factor is not going to change when we're really smooth. Okay. This next one will shock you. What?
The next one. Oh wait, it's here. Why would you do that?
What? Go to the next page. Jesus Christ, child. A radioactive nucleus. Travelling away from you. Okay, fair enough. I can believe that. Now we're going to see V. Oh my gosh, it undergoes a beta mission in its direction relative. We get a little spacecrafty firing a missile boy. U prime is 0.65. And we'll just draw him as a wee.
I'm just gonna have to do this every time. Do missile boy.
Yep. Well, that's it.
As long as it works.
So again, classical relativity says it should be 0.9c. Special relativity says a little bit less. Okay? 0.9?
You want different definitions of a little bit?
0.774. A little bit less. Just a small. All right. That's pretty much it done. We don't need tomorrow's lesson. Let's have a class party. No.
And if we all run around really fast, it'll time dilate. So we'll go for the whole day.
We have enough sugar.
And if you are still confused, put yourself in the alpha particles perspective.
What's it called from Hitchhiker's Guide to the Galaxy? The perspective gun?
If we put ourselves in
I don't know. I read Douglas Adams a long time ago.
I watched the movie.
if we put ourselves in the alpha particle, then what is going back to us?
Well,
You mean the beta particle? The alpha particle and then one which is going away, 0.65.
well, the alpha particle would be measuring V and U, and we would be solving for U prime. So if we're the space cowboy on the alpha particle, then we measure that is V, that is U, and then we were solving for U prime, which should give the same answer as right now.
Oh yeah.
So, what I'm getting at is they will probably ask one question. They don't have enough time to give you a page of questions. You've got, in the 3-hour exam, you'll get one question, and it'll either be a question where you're asking to solve for U or U prime. Now, if you're happy with using these questions, then you go straight to the equation that's in the data sheet, whichever one you want. If you're not happy, then you can do a Galilean transform and go, well, let's put this space cowboy on the missile, or and you can do a shift to use the equation that you're happy with.
So they're not going to ask you to solve from a specific perspective.
They might. That's what I'm saying. From a different perspective, I'll use, as I was talking to Minchin, what if it says, what's the... Well, this is it. This is U. If you were given the alpha particles frame, you would see him travelling away at V, you would see him travelling away at U, and then U prime would be what he observes, because he's given me what he observes the other bloke. That would be U prime. Because U prime is always given to the object that was observed from V that was observed from him. So in the text it says, relative to the remaining nucleus. That tells us U prime, not U. Okay? The way we can change this question, Stan, is let's say an alpha particle travels at 0.25 c. It emits a beta particle, which this observer sees as 0.9. Well, we've just been given u and v. The question might say, at what speed did the alpha particle observe the beta emission? That would be solved for u prime. Well, we've got u prime in the data sheet. There's no need to do a Space Cowboys Galilean transform. Okay? Yes?
What was the first example? Like, which one was? Because the diagram was a bit unclear.
Don't worry about it. Alright, let's have a look.
I think I get it now, but I don't get the first.
Yeah, well, now that you've gone further through the booklet, we can go back and hopefully... Alright, I can stop recording actually. I might try a bit better.